This is the video on the atomic structure. So remember, in these videos, there are going to be codes, two codes. One will be written and it'll be on the screen. The other code will be a verbal code said by myself. Each code will be 3 numbers, and you will need to get all these codes in order to move on with the homework assignment. So in all of these slides, write what's in green. The green is the important part. A lot of information on these slides, but the green is what should be in your notebook, which it just sort of bullet points everything. So this is the weekly review video code, the written code. I would recommend writing this down somewhere. All right, so just to get started, the smallest atom is the smallest unit of matter. We know that it's made up of protons, neutrons, and electrons. Now, the solar system is a good analogy to describe the structure of an atom. We'll go over why that's not the case, but it's just easy to visualize it that way. So let's answer this question: how small is an atom? Well, atoms are really, really small. So it would take a stack of about 50,000 aluminum atoms to equal the thickness of a sheet of aluminum foil, like in your kitchen. Human hair is about 1 million carbon atoms wide. A typical human cell contains roughly 1 trillion atoms. It would take you around 500 years to count the number of atoms in a single grain of salt. So atoms are really, really small. So let's take a look at the nucleus of an atom. The nucleus is located in the center of the atom and contains the protons and neutrons. Now, the electrons are not a part of the nucleus. Now, the protons are the particles that have a positive charge. They are found in the nucleus. They have a mass of 1 AMU, or atomic mass unit. Now, the number of protons determine the number of elements, determine what element that atom is. Now, the neutron are particles that are neutral, meaning they have no charge. They are found in the nucleus of an atom. They have a mass of 1 atomic mass unit as well. They help hold the nucleus of the atom together. Now, the atomic mass is made up of the number of protons plus the number of neutrons. The atomic mass on the periodic table is the average mass of atoms of that element found in nature. So let's take a look at this lithium atom over here. How many protons does this atom have? Well, it has 3 protons. I count up those red spheres. How many neutrons does this atom have? Well, I can count those up. 1, 2, 3, 4. I get 4 neutrons. Well, what would the mass number of that atom be? So I add them together, and I get 7 atomic mass units. That is the atomic mass of this atom. Now, the electrons are particles that have a negative charge. They are found in the electron orbitals outside of the nucleus. Now, they don't actually orbit around the nucleus like a planet's orbit around the sun, but this is how we denote the different energy levels that these electrons have by putting them in different orbitals. Now, valence electrons are found in the outermost energy level of the atom. Now, they determine the chemical properties like reactivity or how the atom reacts. So let's take a look at this carbon atom. How many electrons does this carbon atom have? Well, it has 6 electrons. Now, how many valence electrons does this atom have? So I count up 1, 2, 3, 4. There's 4 valence electrons in that outer shell. So if we look at the electron cloud, it's found outside the nucleus of the atom and is the location of all electrons in the atom. So like I said, electrons don't really orbit around the nucleus. We just use this to denote the different energy levels, but the electrons are, they're in like a cloud surrounding the nucleus. Now, the atomic number tells the number of protons in an atom, and the number of protons determine the identity of the atom. So you can see here's carbon, right? So carbon, the atomic number is 6. It has 6 protons. All carbon atoms have 6 protons. If it doesn't have 6 protons, it is not carbon. Now, isotopes are atoms that have the same number of protons but have different number of neutrons. Carbon has 3 isotopes. Now, notice how all carbon atoms have the same number of protons but have different number of neutrons. Hydrogen has 3 isotopes. Notice how all hydrogen atoms have the same number of protons and have different number of neutrons, right? So you've got 3 different types of these, right? The common one that we use just is carbon, right? It's really easy to look at. All carbon atoms have 6 protons. Carbon 12 has 6 neutrons. Carbon 13 has 7, and carbon 14 has 8 neutrons. Now, isotopes, if you have a silver necklace or jewelry, about half the atoms will be silver 109 and the other half will be silver 107. but all of those silver atoms will have 47 protons. Now, chlorine, if you've ever been in a pool and there's a lot of chlorine, about 3/4 of the chlorine atoms will be chlorine 35, and the other 1/4 will be chlorine 37. But all chlorine atoms have 17 protons, right? And mercury has a lot. We just went over carbon. This brings us to this question: are you really you? So that brings us to the ship of Theseus. The ship of Theseus is a thought experiment that raises the question of whether an object that has all of its components replaced remains fundamentally the same object. But we can simplify it with an axe. So let's just say you have a favorite axe and you are using it one day and the handle breaks. You go out to replace the handle. Well, is it still the same axe because you replaced the handle? The next year you go out and you use the axe and the blade breaks. You go out and replace the blade. Well, is it still the same axe? Like, at what point does it stop becoming that object? So with the axe, there's only two parts. But with the ship, you can replace the planks, you can replace this. It's a lot to think about, right? So why do I ask this? Well, approximately every 7 years, every atom in your body gets replaced. So are you really you? So you can see the pictures over here. They were taken about 10 years apart. Now, none of the same atoms are in these pictures, but like, is it the same person, right? It's just a little thought for you to have a little existential crisis. There's really no right or wrong. It's just like, hey, at what point, as I'm replacing atoms in my body, do I stop becoming this person and become a different person? Because every 7 years, you just cycle most of the atoms out of your body, and it's replaced with new atoms. Same thing with how old you are, right? Well, yeah, we count, when we're born, but all atoms have about the same age, right? So all atoms, with the exception of hydrogen and some helium, were fused together in stars. So we're all about the same age in that sense. And hey, how old are your atoms, right? So we're made out of star stuff. And I put that quote by Carl Sagan: the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made from the interiors of collapsing stars. We are made of star stuff. So we did this class activity, which you identify all those different parts of the atom. You get practice with the first 20 elements on the periodic table and with all the vocabulary and isotopes. So here's a question: how can we see something that is too small to see? And that brings us to Rutherford's gold foil experiment. So Ernest Rutherford, he did this experiment where he had this thin strip of gold foil, and he fired alpha ray particles, very small radioactive parts, and he expected all of them to go through based on his understanding of the atom. Now, that's what happened to most of them, but 1 in 8,000 got ricocheted or deflected. He came to the conclusion that the positive charge, those protons, must be at the center of the atom, and the atoms are mostly empty space. At this time, I'll go ahead and give you that verbal code. The verbal code is 506. I say that again: the verbal code is 506. So we answered these questions. We watched this video, answered these questions. This was the pre-lab. And just basically talking about this experiment. It really does set that up. And we did this experiment in which we were launching pennies at unknown masses, and based on the number of shots, how many times you hit the masses, how many times you missed, you were able to calculate the diameter of those unknown masses, just like Rutherford did. So just as a final thought, remember, there is just too much unknown in the universe to take a break from learning. Get out there and question everything.